So in this video, we're going to be learning how to read and understand velocity time graphs, such as understanding what causes the motion depicted by this line on this particular graph. And we're going to be taking advantage of our experience with position time graphs and understanding the slope of a line in mathematics class so that we can understand how to read and interpret graphs such as these. Okay, I've pre-recorded for you some graphs where we've used the motion detector to measure the position time of a box moving in front of it. Simultaneously, we'll get to see what happens to velocity on this graph down here. So the first graph that we're going to be looking at is the motion of a stationary box that's just standing still in front of the motion detector. Terrific. So what does this show us? Well, what this shows us is that at time 0, my position was 0.3 meters away from the motion detector. At half a second, my position was 0.3 meters away from the motion detector. At 1 second, at 1.5, at 2 seconds. So throughout this whole thing, my y equals 0.3 meters. That makes sense because I'm stationary. Well, when we go down and we look at the velocity time graph, what we notice is that we also have a horizontal line. But in this particular case, the horizontal line here, my y here, equals 0. Well, that also makes sense because in this case, my units are meters per second. So I have a stationary box. It doesn't change position over time. The slope of this line is 0. So what we're going to see down here is we're going to see that this is going to reflect the slope of this line up here. And that's because a velocity time graph is measuring velocity. And we know that the slope of a position time graph is equal to its velocity. All right, what we're going to do now is we're going to be, God dang it. All right, the next thing we're going to do is we're going to try to see what happens when we move the box at a constant speed away from the motion detector. Excellent. All right, our position time graph looks exactly like what we would expect. We see that we have a diagonal line here. We can calculate its average speed by figuring out what its final point was. So our rise was 0.5 meters and our run was 2 seconds. So we could calculate our average velocity as 0.25 meters per second. When we go down and we look at what this line tells us, we notice that this is also more or less a horizontal line. And that horizontal line comes to pretty close to what we just calculated our average velocity is, to be 0.25 meters per second. That makes sense because this is a velocity time graph. And we know that the slope of a position time graph shows us the velocity. And so we would expect a horizontal line on this graph. The graph that we get when we move our same box at a constant speed away from the motion detector, but at a faster rate. So let's go ahead and try that and see. So that's great. We now can see that we were successful in going faster because my final position, my final distance that I traveled over the course of the 2 seconds was much farther. So if I calculate what my average speed was, all I need is my rise, which I think is about 0.7 meters, and I divide that by 2 seconds. So I get 0.35 meters per second. If I look down here, I also know that I went faster because this horizontal line showing my velocity is higher up my chart than my original blue line. So my original blue line was about 0.25. This is showing that it's like about in between 0.3 and 0.4, so about 0.35 meters per second. We also have this added bonus of knowing that for the first half of second, my box was stationary, it didn't move, it just stayed in the same position, and then it started going at a constant speed away. The next thing that we want to explore is we want to see what happens when we move our box starting at a high position and we move it down towards our motion detector. We understand that the position time graph is going to go down and it's going to have a negative slope. Our question is what's going to happen to our velocity time graph here? So let's go ahead and try that out and see. Terrific. So there's absolutely no surprises here on our position time graph. That was exactly as we expected. So in order to find out what our velocity is, our average velocity, again, we need to find the rise, and in this case it's going to be a decrease. So that is 0.4 meters minus 0.6 meters. I'm doing that by figuring out what these 2 points are. And that's divided over my time, which is 2 seconds. So in this particular case, I'm going to get 0.1 meter per second, but it's going to be a negative value. And that, again, agrees with our understanding of what a negative slope is. Well, so in this case, since our average velocity is negative 0.1 meter per second, remember the negative value is indicating direction. So we go down here and we look at our velocity time graph, and we know that this is our 0 meters per second. And what we notice is different about this graph is that our line is below our 0 region. And that makes a ton of sense because any line up in this direction, that is going away from the motion detector because that's a positive velocity. And any direction down here in the bottom is going toward, because that's a negative velocity. All right, so let's have a little bit of fun here. Now what we're going to do is we're going to see what happens when we move our box first away from the motion detector and then back towards the motion detector. So here we go. So this is great. We can see on our position time graph that this portion of the line is got a positive slope. So that's showing that we have a positive velocity because it's moving away from the motion detector. We also notice down here that same motion is registering in a positive velocity as well. So we have a positive here, also showing us that we're going away from the motion detector. Then we start to change direction. We have the motion detector going away, and then we bring it back towards the box, back towards the motion detector. And so that's shown over here by a negative slope, which also makes sense because down here we get a negative slope, and that's because we're going to the motion detector. All right, there's one last thing that we can analyze in this particular graph and get. And that is when we look at the time period between 1 second and 1.5 seconds. What you'll notice in this time period here is this is when I'm going from a positive velocity and then I'm changing and going into a negative velocity. So in this particular situation, I'm changing my velocity. That's expressed down here by a diagonal line. And just like we can use slope and position time graphs and we can infer our velocity, the slope of a line in a velocity time graph also gives us important information. So in a position time graph, remember that the slope of the line is equal to our velocity because it's the rise, which is in meters, over the run, which is in seconds. And so that ends up being our units of meters per second. Well, the same thing applies here. If I'm going to calculate the slope of this line, okay, I'm going to get something else. Here, my rise is velocity, so that's meters per second. And my run is still time in seconds. So now my units are something called meters per second, or meters per second squared. And these units are something totally different. That's a quantity called acceleration. So what I want you to notice is this period here where I have a slope that's less than 0, greater than or less than 0, it's showing us my acceleration. And that makes sense because during this time period I'm changing velocity. And so that helps us understand what exactly is the concept of acceleration. From the previous video that you watched, we understand that acceleration can be defined as the rate of change in velocity. And we also understand that velocity can change in one of three ways. One, we can increase speed. Two, we can decrease speed. Or three, we can change direction. The video also showed us the formula of acceleration is the final velocity minus the initial velocity divided by the time. On a graph, this is exactly the same thing, only this is expressed as the rise over the run. So what this tells us is that the slope of a velocity time graph is equal to the acceleration of the object. So if we go back to our familiar three lines where we looked at originally when I said, hey, you understand what this line is in math because you know it has a slope of 0 and it's basically y equals 4. And you understand what this red line looks like because that has a slope of positive 1, y equals x. Likewise, the green line has a slope of negative 1 and y equals minus x. But because this is a velocity time graph, and now all of a sudden our y values and our x values mean something different, what this is telling us is that we have a slope of plus 1 meters per second squared. So our acceleration is 1 meter per second squared. Well, what does that mean? That means every second the object is going faster by 1 meter per second. After 2 seconds, it's going 2 meters per second. After 3 seconds, it's going 3 meters per second. After 4 seconds, it's going 4 meters per second. After 5 seconds, it's going 5 meters per second. In this particular line, this is showing us that my acceleration is 0. There is no acceleration. So what does that mean? That means that the object is moving at the same speed, 4 meters per second every second. At first seconds, its speed is 4 meters per second. 2 seconds, it's 4 meters per second. 3, 4, 5, 6, it's all 4 meters per second. Likewise, if we look at the green line, we now understand that because it has a negative slope, it has a negative acceleration. In this particular case, it's showing us that we have a decrease in speed. So at time 0, I'm going 6 meters per second, but then every second I go 1 meter per second slower. So at 3 seconds, I'm going 3 meters per second. At 5 seconds, I'm going 1 meter per second. And at 6 seconds, I've stopped. So understanding how to read basic graphs help us to understand both position time graphs and velocity time graphs. So I know this was a lot of information, and in class, we're going to go ahead and we're going to go over some problems, and we're going to do some practice about reading these velocity time graphs.